Hey everyone, and welcome to our first lesson in our unit on organic chemistry. Today will be an introduction to organic chemistry, where we'll learn that organic chemistry is all about the carbon. So today we will learn some properties and how to identify hydrocarbons as either an alkane, alkene, or an alkyne, and we'll talk about the differences between those three. And we will learn how to draw a structural formula for those three types of organic compounds: alkanes, alkenes, and alkynes. Now, what is organic chemistry? Organic chemistry is the chemistry of carbon and any carbon containing compound. Once we understand the basics and how to use a few of the different tables and the reference tables, it's one of my favorite topics to learn in chemistry. We'll learn how to name and draw things like 1,1,3-trimethylbutane and know what they are and what their properties are, how they're going to interact with other things. This really is a basis for a lot of other disciplines in science as well as in medicine. And if you decide to take chemistry in college, this will definitely be a class that you will take if you are studying chemistry or another science or anything in a medical field. It's a pretty common class to take. Now, some properties of carbon compounds. Well, first, carbon has a electron configuration of 2-4, which means it's looking, we want 8 valence electrons, so it's looking to make 4 bonds. So carbon likes to make 4 covalent bonds, which can either be a single, a double, or a triple bond. And that's due to the 4 unpaired valence electrons that every carbon atom has. This gives a carbon compound what we call a tetrahedral arrangement. And if you remember from back earlier in the year, that means that we're going to have one atom making 4 bonds in what looks kind of like a pyramid shape. That's our tetrahedral arrangement. Now, most organic compounds are going to be nonpolar or very weakly polar. So most organic compounds are going to be related to things kind of like oil, which would be nonpolar. And most organic compounds are miscible or mixed with nonpolar compounds or oil-containing compounds very easily. And because of that, they have low melting points and low boiling points. This is why things like natural gas, which is an organic compound, is a gas at room temperature. They have very weak intermolecular forces holding their molecules together, which lowers that melting and boiling point, which also gives them a high vapor pressure, which means they're volatile. These substances can turn into a gas very readily, which if you have flammable or volatile gases around, that could lead to an explosion or a fire. Now, there are currently only about 60,000 inorganic compounds that are known to exist, but there are literally millions of organic compounds. So this branch of chemistry contains a whole lot more information and a whole lot more things to understand and to learn when we compare it to inorganic chemistry. And a lot of these compounds are found as part of biological processes in a lot of different organisms. And that's kind of where we get the name organic. Now, as I said, since most of these carbon-containing compounds are largely nonpolar, they are not going to want to mix, or they're immiscible or insoluble in water. So if we find a solid substance that is soft, has a low melting point, this immediately makes me think of butter, and does not dissolve in water, then it's very likely an organic solid. Also thinking of something like wax. Carbon compounds undergo combustion, which is a type of organic reaction, which we'll learn more about later in this unit. So it's a type of organic reaction. which uses oxygen to produce carbon dioxide and water, and, which is not indicated here, a whole lot of heat. We use these carbon compounds through combustion to produce a lot of the energy used in the United States, whether that is through a carbon containing compound like coal, natural gas, propane. These are just a few examples of carbon containing compounds that we use for energy production in power plants, through generators, through, it could be through food, through cooking, heat. Although very few people probably heat their homes with coal anymore. It is mostly used for energy production as far as power plants. And this can be both good and bad. These substances, these components, these carbon containing compounds like coal, natural gas, and propane are pretty readily available, and they're, for the most part, pretty cheap. But they come with a fair amount of cons, which in this day and age, you got to certainly think of global warming and climate change, which can be linked to the combustion of carbon compounds like natural gas and coal. They're generally considered pretty dirty due to the emissions that are given off. Because often, these CO2 and water are not necessarily the nastiest things, but this is with perfect combustion. Oftentimes, these are not the only two things coming out of a reaction with a carbon-containing compound. For example, it's not only CO2 and H2O that's coming out of the tailpipe of your car when you are combusting gasoline. Now, over time, these compounds, these carbon-containing compounds, will decompose in the ground without oxygen to form component elements. And this is where we get crude oil. Over time, these substances are formed when a once carbon-containing organism gets buried into the ground, is heated, and is decomposed and turned into its component elements. And this takes a lot of heat and a lot of time in order to break down into its component elements, and then later dug up and used through the extraction of crude oil from the earth. Now, most organic reactions have a fair amount of steps in the mechanism that make the reactions complex and slow. So we often have to use catalysts in order to get them up to a somewhat of a usable rate in order to use them in things like industry. Now, these organic compounds are formed by covalently bonding nonmetals. So this is going to be a relatively slow process because covalently bonded compounds generally react pretty slow when compared to ionic reactions, which occur much faster. Now, hydrocarbons, which we'll focus on for pretty much the remainder of this lesson, are molecules that are made only of carbon and hydrogen atoms, which you might think, well, it's got to be relatively easy, but they come in a lot of different forms. They can be simple molecules like methane, otherwise known as natural gas, or having the formula CH4, to propane, which is a 3-carbon compound, or butane, which is a 4-carbon compound, all the way up to octane, or gasoline, which has 8 carbons, or any number of thousands of other molecules. And these hydrocarbons have been the backbone to our energy industry for a pretty long period of time, several hundred years at least. Now, they come out of the ground all mixed together in the form of crude oil, and that's what we pump out of the ground. The crude oil is shipped to a refinery, where the refinery uses a process called fractional distillation to heat the crude oil. And over time, as that mixture is heated, remember, distillation uses the property of boiling points to separate out different components of this mixture, the mixture being the crude oil. And as the temperature rises, different substances are going to boil off. Natural gas would likely come off first, if it's even in the crude oil, since it has a very low boiling point. And as we move up to more complex hydrocarbons, propane, butane, octane, and the boiling points rise, those different components will boil off as the boiling point is reached. These different components could then be collected, and we get things like wax, tar, gasoline, and a number of other different organic compounds that would be contained in the crude oil. Now, a little overview of a few different types of hydrocarbons. Now, these hydrocarbons can be either aliphatic, meaning that they're a straight chain hydrocarbon, or they can be aromatic, meaning that it's a closed chain hydrocarbon or a ring. So these ones are going to be straight chain, aromatic are going to be closed chain. And the aliphatic, which we're going to focus on mostly, can either be saturated or unsaturated. And if we're saturated, it simply means that every carbon-carbon bond in the, in this case, alkane, is going to be a single bond. And that's the key for being saturated. We've added on as many hydrogens, which we'll talk about in a second, to that chain as we possibly can. It's been saturated with hydrogen. Alkenes, which are unsaturated, or alkynes, which are unsaturated, are going to have a triple or a double bond somewhere in its structure. Now on table P, we're given prefixes that will help us identify how many carbon atoms are contained in the particular molecule. We always count the longest unbroken part of the chain to determine how many carbons are in that molecule. So heptane, heptene, heptyne, heptanol, heptanal, heptanone, heptanoic acid all have 7 carbons because they have the hept prefix, meaning 7 carbon atoms. Now, any saturated hydrocarbon only is going to have single carbon-carbon bonds, and that's only between the carbons. Saturated and single both start with S. And these are going to be what we call the alkanes. And they have a general formula of CnH2n plus 2. So we can figure out, if we know that a particular, let's say, methane would have 1 carbon, we know that we're going to have 2 times 1 plus 2 number of hydrogens, or a total of 4. So that's why we're given the general formula. And we can find the general formula along with the name and an example of each type, including the structural formula of a representative from alkane, alkene, and alkyne. And this is on table Q. This is an excellent table to be aware of and be comfortable with, and indicating the number of carbon atoms, which we'll identify based off of the name. Ethane, F meaning 2. So we have 2 times 2 plus 2, which would be 6. And we have 1, 2, 3, 4, 5, 6 hydrogens and 2 carbons. Now, anytime we see the ene ending, that's going to indicate that it's an alkene, and therefore there's going to be a double bond somewhere between carbons, and we'll have to identify where that is. When you see the ine ending, that's going to indicate a molecule that's part of the alkyne family, and an alkyne is going to have a triple bond somewhere in the molecule. Now, the larger a hydrocarbon is, the more complex molecules, they're going to have higher boiling points because they're going to have higher intermolecular forces. The forces between larger molecules are going to be stronger, which is going to lead to a higher boiling point. So, for example, here, CH4 is methane. It turns into a gas at a minus 161 degrees Celsius. Meth meaning one carbon. Ane meaning it's an alkane, so it's all single bonds. So our structural formula is one carbon, and then we just fill in the remaining bonds with hydrogens. And as long as it's a hydrocarbon, it's only going to contain those two elements. C2H6 contains two carbons. This fits the CN H2N plus 2 general formula, meaning it's an alkane. Two carbons would be F, so this is ethane. And now that we have two carbons, you can see the boiling point is getting less negative or more positive, so it's rising. Alkanes only have single bonds between the carbons, and we have two carbons, and then we connect and make the remaining bonds with hydrogen. So if we look at a carbon here, it always needs to have four bonds. We have 1, 2, 3, 4. We always want to make sure that that is set up that way. Now the third one here, C3H8, there's three carbons. The prefix for that is prop, and it fits the general formula for an alkane, so this is propane. Boiling point continuing to rise. It's almost twice as high as ethane. And it's a bigger molecule. Prop meaning three carbons, part of the alkane family. So therefore it's all single bonds, and the remaining bonds are filled with hydrogens. So let's try this. What's the molecular formula for octane? Now we'll first identify, when we look at this word, the name. It ends in ane, so it's an alkane. And the prefix is oct, which means it's going to contain 8 carbon atoms. Now you can feel free to pause this video at any point and try these and check your work. I'm going to number these. You'll see why later. 4, 5, it doesn't really matter which way you go. And it's an alkane. So we have all single carbon bonds. We have 8 of them for the oct. And then we just got to make 4 bonds with every carbon. What happened there? Octane's a lot, and I'll give you a shortcut on this in a minute. Now, generally we write all the hydrogens in here, which, as you can see, watching this video or even doing it yourself, is pretty annoying. But nevertheless, I want you to see how you would do this, and I'll show you a shortcut in a second. So we double the 8 and add 2, and this gives us 18 hydrogen atoms, and we connect those to each of the carbons. So our formula becomes C8H18, and we just fill that in with the general formula shown here. Now, an unsaturated carbon is going to have at least one double or triple carbon-carbon bond, and that's going to be our alkanes and our alkynes. So if it contains a double bond, it's going to be part of the alkene family, and if it contains a triple bond, it'll be part of the alkyne family. We want to check table Q for any information on either of those two types of hydrocarbons. So as far as the alkene family, we could have one or more carbon-carbon double bond. Now, any molecule that has more than 4 carbons, like butene, or anything larger than that, is going to allow for the placement of a double bond at different spots along the chain. These are what we call isomers, not to be confused with isotopes. The isomers are molecules with the same molecular formula, but a different structural formula. It's kind of like a Lego set of 10 pieces. They all contain the same components, but you can put them together in a bunch of different ways. So we have the same molecular formula, the same components, but put together in a different way. Now this general formula shows that we have twice as many hydrogens as we do carbons, but it's not H2n plus 2, it's just H2n. Now the lowest numbered carbon that touches the double bond has to be identified. Now we could number this as 1, 2, or we could number it as 1, 2. It doesn't really matter. It will once we get to longer or bigger hydrocarbons, but for now, this one is fine. So no matter which way we number this, the double bond is touching the first carbon. So we identify that it is a 2-carbon compound, so it gets the prefix F, and it gets the ending ene or ene because we have a double bond here. So this is ethene, and the double bond is always on the first carbon, so we're not going to identify that. But in the next example here, we number here 1, 2, 3, or it could be 1, 2, 3, and we can see that this is not quite too different. So we have, depending which way we look at this, there's only really one other orientation, but it's not really going to matter, because this molecule, we can go into the screen and look behind it. This double bond is always going to be on the first carbon. So if we numbered it this way or we numbered it the other way, it's always going to be in between the first and second carbon. We want that because it's always got to be on the lowest number. If we go the other way and we number 1, 2, 3, this double bond is going to be between the second and third carbon. So this is propene because we have 3 carbons, so it gets the prop prefix, and it ends in ene because we have a double bond. And that double bond will always be between the first and second carbon. Even if we were to put that over here, we could look at this from behind the other way, and it's still going to be the same orientation. Now, if we have more than 3, in the case of a 4-carbon compound or molecule, depending how we number this, this can be very different. And if we flip this around and go to the back, it's not going to be the same thing. So to start, since we have a double bond, we know that it's part of the alkene family. So the ending is going to be alkene. There are 4 carbons, so it's going to get the but prefix. So this is butene. But the only difference is that we have to identify where this double bond is. We always put it on the lowest numbered carbon that's touching the double bond. In this case, it will be 1. So this is 1-butene. In the second example, we see the double bond gets moved in between the second and the third carbons. Therefore, in this case, it doesn't matter if you number left to right or right to left. It's always going to be 2-butene. So the only difference between these two is the placement of the double bond, but that does in fact change what the substance is, and therefore changes its properties. So these are considered isomers of butene because they are all have the same formula, C4H8, but the placement of the double bond is different. So a little example here. We'll do a few of these. On the top, we first identify how many carbons we have. We have 1, 2, 3, 4, 5. So we get the prefix pent. We have 1 double bond here, so it's part of the alkene family. So this is pentene. And we have to identify on which carbon that double bond is. And we can either start with 1 here or 1 here. If we start with 1 on the left, the double bond is touching the first carbon. If we start with 1 on the right, the double bond is touching the 5th or the 4th. So we want to start numbering from the left. So this would be 1-pentene. So we have a double bond between the first and second carbons. Second example, again, we start with how many carbons we have. There's 5 there, so that's pent. We have a double bond, so it's pentene, but the double bond is moved from the first to the second. If we number it the other way, that would put the double bond in the third. So it can either be on the second or the third, depending how we number these. And we want it on the lowest. So this would be 2-pentene. And for the last example here, if we number left to right, it's going to be different than if we numbered right to left. And now this one, the third example here, is like looking at the second one backwards. If you were to go into the screen and look back at yourself through this molecule here, it would look just like this one. So this is still 2-pentene. Just depends on which way you're starting to number from. But all of these are considered isomers of pentene. Now let's draw the molecular formula of 1-octene. Feel free to pause the video and check your work. Now, oct means that we have 8 carbons, 4, 5. And ene means that we have, it's the alkene, and we're going to have a double bond in there. And the number tells us in the name where it is. And it's located on the, this should be a C. Yep. And the double bond is going to be located on the first carbon. Now, it doesn't matter which one you call the first carbon. I'm just going to call it this one over here. So put the double bond there. And the only other thing we have to do is fill in the remaining bonds. Each carbon should have 4 with hydrogen. And what I'm going to do is just draw the bond and not drawing in the hydrogen, because we'll assume, since this is a hydrocarbon, that each of these is bonded to a hydrogen. And it's just a little shorthand notation of writing this. Now this carbon that I have not filled it with hydrogens yet has already made 3 bonds, so this one only needs 1 more. So I'm going to put 1 there, and this one on the end has 2, a double bond there, so it's going to need 2 more. And then just to verify, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens, which fits the CnH2n general formula. So our formula becomes C8H16. Now the last one for today is the alkyne family. If it's part of the alkyne family, it's going to contain a triple bond. Now, just like the alkenes, if we have 4 more carbons, we can form isomers. And the general formula for an alkyne is going to be CnH2n minus 2. So similar to an alkane, but it's minus 2 instead of plus 2. And alkynes will always contain a triple bond somewheres in their structure. But the naming is still the same. So we have 2 carbons, so our prefix is F, and we have a triple bond. So it's part of the alkyne family, so this is ethyne. And we don't include a number of where the triple bond is because it can only be touching the first carbon. Same thing with the second one here. This is propyne, because we have 3 carbons, and the triple bond is always going to be on the first. And you think, well, what if I numbered it this way, 1, 2, 3? Well, these are 3-dimensional molecules, so no matter which way you're looking at it, the triple bond is always going to be on the first carbon. Now, trying to name these, we start with number of carbons. We have 4, so this is bute. We have a triple bond, so it's part of the alkyne, so this is butine, and we're going to number the lowest numbered carbon where this triple bond is, which would either be a 1 or a 4, depending on how we started counting, left to right or right to left. So we'd want to put it on the first or the lowest numbered carbon. So this is 1-butine. And the second one, also 4 carbons with a triple bond, so it's also butine, but this time it's in between the second and the third, so we'd call that one 2-butine. And these 2 are going to be isomers of butine since they have the same components, just in a different structural arrangement. Now a little practice. we have 5 carbons, so this is a pent molecule. With the triple bond, it becomes pentyne, and that triple bond is on the first carbon, which would give us 1 pentyne. And the second example, we have 5 carbons, but we've moved the triple bond in between the second and the third carbons. So we still have pentyne, but this one is going to be 2 pentyne since that triple bond is in between the second and the third, and we identify it on the lowest number carbon possible. So that's 2 pentyne. Now we'll do a little example here. What's the molecular formula of 2-octyne? So I'm going to start by drawing this. So we have octyne, which means we have 8 carbons. And since it's part of the alkyne family, it's going to have a triple bond on the second carbon. And you can do this either direction. I'm going to put this one here. And since it's 2, if you put it in between the first and second one here, it would be numbered 1-octyne. So I want to make sure it's in between the second and the third. Since we have 8 carbons, we have H2N minus 2, which gives us C8, H28 minus 2, which is C8H14. So we have to put in 14 hydrogens around here, which as long as we make 4 bonds with every carbon, we should have that. The tricky ones come where we have the triple bond. Now this carbon right here already has 4 bonds, as does this one. It's got the triple and the single, but the one on the end is going to need bonds as well. So we have 8 carbon atoms for the prefix oct. We fit the number of carbons into our general formula, and we get our formula is C8H14. We'll do a fair amount of practice with this, but the rules are pretty straightforward. If you guys have any questions, make sure you come see me and get your questions answered. Have a great day.